So last time we were working on this limit that involves this indeterminate form infinity minus infinity. So, very quickly here, we notice that this is a limit problem. And first, I think one thing it's important to notice is that this is a limit problem. It's a one-sided limit where x is going to a finite number. So typically in a case like this, dominance of powers is not going to come into play. We would typically use a technique like dominance of powers if x were going to infinity or if x were going to minus infinity. So one thing to notice is this is a one-sided limit. And if we apply the limit, for example, for this first term, if you plug in, you get 1 over 0, which is our number over 0 form. And in a limit, in a one-sided limit, number over 0 is either plus or minus infinity. And now you remember x approaching 0 from the right, in particular, means x is greater than 0. So if x is greater than 0, this first term here, this is going to go to infinity. This first term is going to go to infinity. I copy the minus sign, and it's the same idea for the limit of 1 over root x. As x goes to 0 from the right, you get 1 over 0. So in a one-sided limit, number over 0 is either plus or minus infinity. Here, this is a positive term. And also we see another reason here for taking the limit as x approaches 0 from the right. Because of the domain restriction here from the denominator, we can't take a limit as x approaches 0 from the left or a two-sided limit. Approaching x from the left wouldn't make sense here because we can only take the even root of a non-negative number. But anyway, this second term also goes to infinity. So this is this infinity minus infinity type indeterminate form. And once we get that type of indeterminate form, that just means we need to do more math. In this case, I think it's very important just to notice from an algebra point of view, these fractions can still be combined. So here, I try to do the limit, and I try to plug in, I get infinity minus infinity. And so now I'm combining the two fractions. And so I was being a little bit silly. I don't know why I did this when I worked out this problem. I didn't think it through. I think I was being a little bit on autopilot. I just multiplied the first fraction by root x over root x. And I multiplied the second fraction by x over x. But that's kind of more work than necessary. I should have been a little more in the moment and simply just multiplied the second fraction by root x over root x. No matter, as long as I follow the valid steps of math, I should get to the right answer. So maybe, you try it this way at some point just to see if you get the same answer. So I multiplied the first fraction by root x over root x, so I get a root x on top, minus, and then I multiply the second fraction by x over x. So now I have root x minus x over x root x. And so now try applying the limit again. If I try to apply the limit, I get 0 over 0. And so again, 0 over 0 is an indeterminate form that just, is feedback to the user that says we need to try something different. We need to try more math. And here, because of this form, the root x minus x, the hint here is to multiply top and bottom by root x plus x, the conjugate. And so when I multiply by the conjugate, a minus b times a plus b is a squared minus b squared. So upstairs I have root x squared, which is x, minus x squared. Downstairs, it's a bit messy, and I should have done the simpler denominator. Just multiplying the second term by root x over root x would make the denominator a lot simpler, but it's okay. We can still sort this out. So downstairs, what you should notice is that there's some math to be done here. So by the way, if I apply the limit, if I try to take the limit now, I still get 0 over 0. So what I'm going to do is I'm going to factor out the common terms. So let me show you how the factoring goes in the denominator here. I just want to back it up one step. So here, I'm going to factor out a root x. And factoring out means we're dividing each of the terms by the thing we're factoring out. So here, root x over root x is going to be a 1 plus x over root x is going to be a square root of x. And on the outside, I'm going to have a root x that I factored out, but I already have these two terms there as well. So I have a root x and an x. So these two root x's combined, root x times root x becomes x, and then x times x becomes x squared. So in the denominator, we end up with this. So here you have the x squared. This is from when we, so first we factor out a root x, so that becomes a 1. Factor out a root x, that becomes a root x, and then on the outside, root x times root x is x, x times x is x squared. So that's where all that mess comes from. And yeah, it's a little messy, but it's also good algebra review. You know, whether the problem's messy or not, we should be able to dig our way out just by doing the math and, you know, not letting it disorient us, because that can definitely happen. And of course, practice makes perfect. So here, if I tried to apply the limit, it would still be 0 over 0. Of course, we see there are simplifications to make. So even before applying the limit, I can cancel the x in the numerator, and I can cancel one of the x's in the denominator. So when I do that, that's what the limit looks like. And now let's apply the limit. Now be careful, this is x going to 0 from the right, so I can't use dominance of powers here. Here, I just want to plug it in. When you plug 0 in the numerator, I get 1. I get 1 in the numerator. In the denominator, I get 0. So this is a number over 0 type indeterminate form. That means the limit is either plus or minus infinity. I just need to check the SIGN of this expression for x greater than 0, but very close to 0. You know, so for that, I just plugged in a point. So for example, if I'm looking at the x-axis and 0 is right here, here I'm taking a limit coming in from the right. So coming in from the right. So for example, I just picked like 0.1 to plug in. When I plugged in 0.1 in here for x, 1 minus 0.1 is 0.9, so that's positive, divided by, and the entire denominator is positive, because here you have 0.1 times 1 plus the positive square root of 0.1. So the entire denominator is positive. So I have positive over positive. So this number over 0 in a limit gives me plus infinity here for this one-sided limit. So this limit problem is a little tricky. And I like it because it makes us think about a lot of our different limit theory, you know, so you should work through this and just make sure all the steps make sense to you. So this, so the last thing I want to talk about here when talking about limits is the types of divergence. So first of all, remember that we say a limit exists if it equals a finite number. That part is really important. That's the only way a limit can exist. So the limit exists if the limit is equal to a finite number. And another word for saying the limit exists is to say that the limit is convergent. You think about what that word convergent means just in regular language, right? It's when things meet. So here the limit is converging to its, you know, to its limit. If the limit does not exist, if the limit does not equal a finite number, then the limit does not exist, or the word we use is the limit is said to be divergent. So divergent and does not exist, that's the same. They're synonymous. Limit does not exist, or the limit is divergent. So now that we've got infinity in the picture, I want to talk about the different ways a limit can diverge. So in fact, now there are 4 distinct ways a limit cannot exist. The first way is if the limit just gets bigger and bigger and bigger and never stops getting bigger. So in that case, we say the limit grows without bound and that the limit is positive infinity. And here I didn't write anything down here. This could be x going to infinity or x going to a fixed number. So I didn't write anything down here. But if the range function, you know, if our range value of our function is blowing up to infinity, then the limit does not exist. I don't want to write DNE if I can be more specific than that. If I can write plus infinity or minus infinity, that's what I want to do. I want to give as specific an answer as possible, because in math we want to be precise. So if I can give you more precision than just the phrase does not exist, then I'm expected to do that. Again, if the limit grows without bound to negative infinity. So here, again, the limit does not exist. Negative infinity, remember, is not a number. Infinity and negative infinity are behaviors. Infinity is the behavior of just constantly getting larger and larger and larger. Negative infinity is the same thing, but in the opposite direction, right? You get bigger and bigger in the negative direction. And remember, there are different types of infinity. The function x goes to infinity, the function x squared goes to infinity, but one function goes there a lot faster than the other. So there are different levels of infinity. A third way, and this is, the main thing we had studied in the theory before we'd brought infinity into the picture, was for a regular two-sided limit. If the limit from the left and the right doesn't exist, then the limit doesn't exist. That's kind of the theory we started with. This was before we brought infinity into the picture. Finally, the fourth way a limit can fail to exist is if the limit oscillates forever. So consider the limit of cosine of x as x goes to infinity. Think about the graph of cosine. It just oscillates between -1 and 1 forever without ever actually, approaching one number, getting closer and closer to one number without actually attaining a limit. So a function that oscillates forever, like cosine of x as x goes to infinity, that function, the limit does not exist. And in each case, the way the limit does not exist is different, right? When it blows up to plus infinity, or when it goes to negative infinity, when the limit from the left and the right aren't equal, when it oscillates forever, these are 4 different types of behavior, that we can identify for a limit not existing. So yeah, I think it's important, because sometimes students will think the only way a limit cannot exist is if you have this left and right side aren't equal. But certainly if the limit blows up, that's also a way it cannot exist. Or if it oscillates forever, these are all ways the limit cannot exist. So the limits are extremely important because they come back in a big way in Calc 2. Okay, so that's why we really need to make sure we get our limits down. So this ends the discussion of limits. And so now what we'd like to do is take the limits and do something in calculus with it. Solve a problem using limits. We didn't study limits just for the heck of studying limits. We want to do something in calculus with it. So very famously, all of calculus is motivated by this famous problem called the tangent line problem. And so, the tangent line problem is basically this question here. What is the slope of a curve? Or more accurately, what's the slope of the curve at a fixed point? So I kind of want to go back a little bit and just go back to pre-calculus. And, remember in pre-calculus, given a straight line, we figured out the formula to find the slope of that straight line. Now, the slope of the straight line at any point, so now if I kind of go along any point of this straight line and try to calculate the slope here is always the same. For a straight line, the slope is constant. So, the next question is, okay, well, what if we look at a curve or a line where the slope is not constant? And so, for example, if I have a slope like this, okay, so there the slope is constant. Let me now just randomly change the slope. So then that changes direction. Let me change the slope again. So what I'm seeing is if I look at a graph where I allow the slope to change, the line is no longer a line, but the line starts to curve. And in fact, we would expect based on an experiment like this, that if I had an actual curvy line like this with no corners, based on my experiments, I would conclude that for something that's a curve, the slope at every point is not fixed. If the slope were fixed, then the graph would be a straight line. The fact that the graph is not a straight line tells me from my basic experiments that the slope for a curve that's curvy, the slope is changing. And it's the change of slope that causes the curviness. You know, at this point in calculus, we want to try and understand how a curve curves. What causes it to be curvy? What causes it to be straight? This will allow us to analyze actual physical phenomena. If I'm trying to build a roller coaster, if I'm trying to build a road, if I'm trying to design any kind of air vehicle, satellite, rocket, airplane, the curves, the shape, that all matters. You know, from a production standpoint of view, from a materials point of view, from aerodynamic point of view. For a roller coaster, if it's designed with a curve where the second derivative is not continuous, then that roller coaster is going to be very herky-jerky and could, potentially be a rough ride. So there's actual math that goes into what does a smooth ride feel like on a road or on a roller coaster, and it's connected to the slope. And you'll study this concept called curvature in Calc 3, very extensively. So here we can answer the question, perhaps using limits, right? I would hope that we spent all this time studying limits so that we can, so that it's relevant here. So first I need to define the concept of a secant line. A secant line is any line that goes through 2 points of the curve. So here I have some curve and I've drawn a secant line. And a secant line is just a straight line, like from pre-calculus. So we can calculate the slope in the standard way, rise over run, delta y over delta x. So here the slope, of the line that goes through the point a comma f of a and x comma f of x would be f of x minus f of a over x minus a. So now here's the theory. I want to find the slope of this curve at the single point a, not over these 2 points, not over an interval. So now the theory is very simple. Let's just use a limit. Let's take this second point, x f of x, and let's just make it go closer and closer to f of a. And at each step, let's calculate the slope of the line. So here I'm taking x and I'm making x closer and closer to a. And you should think about what happens to the secant line. So as x gets closer, so maybe this is the next secant line as I'm making x closer and closer to a. So there's one secant line. So you see here at this point, x is a little bit closer, the x-intercept of the x-axis. And then maybe the next secant line's right here. Eventually, as x approaches a, these secant lines are going to coincide with this line right here that's at the point. And that line that's just at the point, that's the limit of these secant lines. So, you should see this secant line kind of swings around and coincides with this line. And that's what this limit is describing, exactly that procedure. So now I think it's really important that you connect up the picture and this limit. So here, this equation is the slope of the secant line. And now we say let x go to a. So that's us taking this secant line and making that second point here for this x coordinate right here get closer and closer to a. And now if the limit exists, we're going to define that number to be the slope at a single point. So that's the theory here. And when you look at this formula, you should kind of see the story that this is the slope of the secant line. And now as x goes to a, we're making the secant line get closer and closer to becoming the tangent line, which is this line that's touching the curve at one point. By the way, it's really, there's this other formula, which is nice to also use. And so I have the other formula here. We've talked about this before. So for the other formula, you can use the change of variables, let x equal a plus h. So here, this x gets replaced with a plus h. And if x equals a plus h, then h equals x minus a. So this x minus a here in the denominator gets replaced with h. They're both exactly the same thing. They're both, the picture here is describing the slope of that tangent line. And we'll use this notation here. It's called the derivative, which I'll define formally in a second, to indicate the slope of that tangent line, m sub t here. So here's a definition. We define the tangent line to any curve y equal to f of x to be the line that goes through the point a comma f of a and has slope that's given by this formula. The slope is the slope of the tangent line. And so here, this is the formula for any line going through the point a comma f of a with slope, the slope of that tangent line. If I use this derivative notation, the formula would look like that. And we can answer our motivating question. So the answer now to the question, what is the slope of the curve at any point? The answer is the slope of the curve at any point is this number m sub t, where m sub t is calculated with this limit. And that's kind of the beginning, the introduction to the idea of a derivative. Because now the question is, okay, what does this limit actually represent? Now we want to start to analyze this thing that we call the derivative and try and, give it some meaning. So I want to do a toy example here, but right off the bat, I'm going to show you something useful we can do with the derivative. And well, I'm going to show you something we can do with the derivative. Whether it's useful or not, I'll let you decide. So here it's asking for us to calculate f prime of 4 using the limit definition. So very soon we'll get some shortcut rules that'll allow us to calculate the derivative rather than using this limit definition or this limit definition. We will skip all of that, okay? So it's important for now, though, for us to pay attention to the instructions. If we're doing a problem that says to use a limit definition, then that's what we'll do. And the limit definition of the derivative is either one of these. These are both the same definition. And for you, you should learn how to go back between one form and the other. And the trick is to use, this transformation here. Remember that my picture is a little biased, by the way. This is a two-sided limit. So remember here, x can approach a from either side. Here I'm being a little biased and my picture's kind of approaching it from the right. So here, using the limit definition, which I've memorized, I can write f prime of 4 is the limit as x goes to 4, f of x minus f of 4 over x minus 4. Now look, if you try to apply the limit to the theoretical definition of the derivative, you get 0 over 0. That's always going to be true. If I plug in a 4 for x, f of 4 minus f of 4 is 0. Plug in a 4 here, you get 4 minus 4 in the denominator. So when you're trying to calculate a derivative using the limit definition, you have to use some kind of mathematical trick. It's always going to be 0 over 0. So here I plugged in for the definition of the function. The function here is positive square root of x. Here, positive square root of 4 is just 2. As I said, if you plug in a 4, you get an indeterminate form of 0 over 0. In this case, because of what's appearing in the numerator, I'm going to multiply by the conjugate. That's the strategy to use here. And you remember a minus b times a plus b is a squared minus b squared. So the numerator becomes x minus 4. And in the denominator, we already had an x minus 4. So I cancel. And now apply the limit. So this 4, I plug in. Positive square root of 4 is 2. So the limit is 1 over 2 plus 2, or 1/4. And in a second, I'll use this information to do something pseudo useful. Here I wanted to do the same problem, but using the other formula. So this is the limit of f of a plus h minus f of a over h, where in this case, the a is equal to 4. So this is the a in our a plus h minus f of a formula. So again, I plug in the function. If you apply the limit and let h equal to 0, we get 0 over 0. This is always going to happen to the theoretical definition of the derivative. And again here, based on the form in the numerator, I'm going to multiply by a conjugate. And here, the numerator, when you multiply, the root 4 plus h gets squared. So I have 4 plus h minus 2 squared, so minus 4. And here you see the 4's cancel. This 4 will cancel with this 4. And I have h over h times quantity root 4 plus h plus 2. And so now we can cancel these h's in the numerator and denominator. Once we do that, we try the limit again. So plug h equal to 0 in here. I get 1 over positive square root of 4 plus 2, or 1 over 2 plus 2, or 1/4. So that's the derivative. You know, we can interpret it in a couple of ways. So one way to interpret it is, so now if I'm looking at the graph of square root of x, I know at the point 4, the slope of the tangent line is, you know, positive 1/4. So I know the slope here is some positive number, 1/4, and that it's increasing function. But there's actually something that's much more useful beyond this geometry problem, the solution of this geometry problem. Here's something that I think is one of the biggest uses of the derivative here. So first, let's think about what this limit means. So as h goes to 0, this quotient, whatever it is, gets closer and closer to this number as h goes to 0. So if h is very, very close to 0, so assume h is a number either positive or negative, but very, very close to 0, like h is 0.01 or whatever. So if h is very small, then I'm going to claim that f prime of 4 is approximately equal, because they're very close. So here I won't put an equal symbol. I'll say it's approximately equal. So when h is small, f prime of 4, what's on the left side, is approximately equal to what's on the right-hand side. So now what I'm going to do is I'm going to solve for f of 4 plus h. Okay, so here I want to solve for this term right here. So that involves, so I'm going to take this h down here, move it to the other side, and multiply it to this f prime of 4. And then I'm going to take this is a minus f of 4, and move it to the other side. The minus becomes a plus. So I get a formula that looks like, so I've written it down here, so let me show you. Here's the formula when you solve. So this formula now, I claim is somewhat useful. And let me just remind you where that came from. Okay, so here I'm approximating f prime of 4 with this, what's called a difference quotient here on the right-hand side. And so if you solve for f of 4 plus h, you get this formula. And so if we apply it, you know, so you say, okay, so what? Well, in this particular case, it gives us a formula like this. The positive square root of 4 plus h is approximately 2 plus h over 4. And so what's the big deal? You know, the big deal is the expression on the left-hand side. This expression here, the positive square root of 4 plus h, that's a theoretical idea. That's a concept that we get. But I can't actually calculate anything. If you look at this expression on the right-hand side, this is an expression I can actually calculate. I don't need any machines or anything. With pencil and paper, we can do division or multiplication, and with pencil and paper, we can do addition or subtraction. So this formula, this using the derivative, I've come up with a formula that allows me to calculate square roots of numbers near 4 using addition, multiplication, division, subtraction. No other math, just using 4-function math. If you look at what's in the blue box on the right-hand side, this does not involve anything other than addition, multiplication, subtraction, you know, and that we can calculate by hand. So for example, suppose I wanted to find the square root of 3.9 because I'm building something and I need to know the square root of 3.9. Well, the square root of 3.9 is the positive square root of 4 minus 0.1, which according to this formula, I can approximate as 2 plus 0.1 over 4. Okay, so 1/4 is 0.25. So 0.1 over 4 is 0.025. Oh, and here I'm subtracting. So hold on. This plus, I need to change to a minus because here I'm subtracting. My h is negative, so this should be a minus. So I need to do 2 minus 0.025. That's my approximation of the square root of 3.9. So let me see. 2 minus 0.025. Is that 1.975? All right, folks, no hands. I'm going to approximate the square root of 3.9 as 1.975. That's no hand. Just boom, no calculator. Anyone out there with a calculator? Can you give me an approximation? What's this positive? What's the square root of 3.9 in your calculator? Anyone? Anyone? Anyone hear me? Is this thing on? Hello? Hello?
Yeah, it's 1.974.
Oh yeah! Woo, woo. That was pure, just done by hand, y'all. And so, you know, this is one of the biggest applications of calculus. You know, so now you're saying, Sajid, why would you do it by hand? Why don't you just use your calculator? Well, as engineers now, you have to ask the question, how does your calculator do it? You know, that's kind of where we're at now. We have to ask ourselves, how does everything work? Yeah, I could just do it in a calculator, but how does the calculator know how to do it? So this idea is a very important one where we're doing these approximations using the derivative. And we will definitely continue this idea in this class, but this will also continue in a huge way in Calc 2. Okay, and for applied scientists, this is really a huge revelation that we can actually use the derivative to come up, you know, with ways to calculate these theoretical mathematical concepts like the square root of something. So, you know, in World War II, the two largest scientific contributions from World War II are said to be the development of radar and the development of the atomic bomb. So at that time in the development of the atomic bomb, we did not have computers, much less very nice calculators, you know. So one question is, without computers or calculators, how were they able to engineer something as complex as an atomic bomb? You know, which required so many precise calculations and complex calculations, not just theoretical answers. Don't tell me the answer is square root of 3.96. That doesn't help me. I can't look up square root of 3.96 on a measuring tape. I need an actual number, you know. So using techniques like this, they were able to by hand figure out a lot of precise calculations. So, you know, right off the bat, this is one huge reason why we're even studying calculus right now. And actually the way the theory works is I can even tell you that my approximation was an overestimate, you know, and I'll show you this next time. But so here to use the derivative that we found in the previous examples kind of for an artificial problem here, I asked for the equation of the tangent line now to the curve f of x equals square root of x at the point 4, 2. So we've already calculated the slope at x equal to 4. And so, you know, we've memorized that the equation of the tangent line is just f of a plus f prime of a times x minus a. Here a is 4, and we said the slope was 1/4. So in this case, just plugging in and simplifying, you know, we can calculate the slope of the tangent line. As a slope of the tangent line, it's really, you know, it's a novelty, great. It's not that useful. But if we use the slope information here in this way to do approximations, then suddenly it does become extremely useful. It becomes more than just we've solved this interesting geometry problem. We're now actually able to, you know, start to potentially do something useful here. So here's the derivative. I'm officially defining the derivative. So, you know, why am I giving you this formula again and saying the derivative of the function? What I want you to think about is that the derivative is its own thing. It's a mathematical creature or a mathematical object that exists on its own. It doesn't care about slopes or tangent lines or velocity, anything. It exists purely as a mathematical creature. Remember that math is a science on its own. It does not have to be useful to justify its existence. It's a science completely on its own. So here, what we're doing when we solve the tangent line problem, when we say, what's the tangent line of a curve at a point? What we're doing is we're solving a geometry problem. And this is the most traditional example of the definition of the word applied math. That word has changed a lot, but traditionally, applied math meant using math from one area of mathematics to solve problems in another area of mathematics. A very famous example would be probability theory, where we use calculus and other discrete mathematics to find probabilities. So here again, we're using this thing called a derivative from calculus to solve a geometry problem, to find the tangent, the slope of a curve at a point, okay? So here I'm defining the derivative as its own thing. And if you want to interpret it as a slope, you can, but you don't have to. It's just its own mathematical object. And it's the usual definition. And I've given the alternate definition in terms of H. And it's very important for you to be able to go back and forth. So here, if we let x minus a equal h, and if you solve for x, then if x minus a equals h, and if you solve for x, x would be a plus h. And going the other way, if I have f of a plus h, if I let a plus h, so if I let a plus h here equal x, then if you solve for h, h is x minus a, and you can completely convert the formula the other way. So you should kind of be able to go back and forth here and be comfortable with both these formulas. They should, at the end of the day, calculate exactly the same information. And of course, because this is a limit, all of this only makes sense providing the limit converges or the limit exists. And you know, some applications, so applied math. In geometry, the derivative represents a slope. But to say the derivative is a slope, that's not true. The derivative is its own thing. You know, yeah, it's a slope when we interpret it from a geometry point of view with graphs and whatnot. If f of x, instead of being the height of a function, represents the distance traveled by a vehicle, and if x, so f of x is the distance traveled, and suppose x is the time in hours. One great exercise is to think about the units of our derivative. So in this case, the units of the numerator will be distance traveled, let's say miles. And here, the denominator will be time, which is in hours. So here, this would be miles per hour. And so in this case, I can interpret, oh, the derivative would represent a velocity. You know, think about what miles per hour represents. Use the units of your numerator and denominator to find the units of the derivative and use that to help you understand what the derivative is doing. Now suppose f of x is still the distance traveled, but now suppose x is the number of gallons of gasoline used. So now if you check, the numerator will be distance traveled, like miles. The denominator will be gallons. It will be miles per gallon. So in this case, the derivative would represent miles traveled per gallon. And you know, it's not representing a slope anymore. These are three different applications of this calculus math object called a derivative. Here's an interesting application. If x is the amount of money accrued in a bank, f of x is the amount of money and x is the time, then the units of our derivative would be dollars per year, and the derivative would represent, you know, dollars per year earned or lost. If the derivative is positive, then we're, you know, gaining money. If the derivative is negative, then we're losing money. If the derivative is zero, we're neither gaining nor losing money. This is an interesting application because the domain here for x isn't necessarily a real number. So I'll come back to this point, but this third example is a little weird because x isn't necessarily When we talk about money, we can count money, $1, $2, $3. It doesn't necessarily go on an x-axis, right? Money. So I'll come back to this point later. It's a very subtle point. It's about discrete numbers versus real numbers, and I'll come back to that. So here is the, I guess, most famous example of applied math where we use calculus to describe physics, rectilinear motion. So this goes back to the story of Newton sitting under the tree, and he gets hit in the head by an apple, So at this point of time in history, the other thing I really want you to keep in mind when we're studying calculus in this class, this isn't just a math class, this is also a history class. We have to keep in mind the technology that we have access to during this time of math. And all of this math we're doing, there's no machines. And so when we're doing that, we should keep that in mind. I mean, also there's no calculators in that class, but just in general, during the time of history. So that's part of the obstacle we're trying to get over. We're trying to figure out, how do you figure out the square root of 3.9? Because a calculator hasn't been invented yet, okay? So here, at the beginning, physics and math right now are basically the same thing as Newton is trying to figure this stuff out. So, we define, so let f of t represent the position of an object moving in a straight line. And remember that distance is rate times time. So here, we can first think about what's the average velocity of the object over a time interval. So here I want to know what's the average velocity between 5 and 10 seconds, for example. What's the average velocity of an object between 5 and 7 seconds? And so we say the average velocity because distance is rate times time. So velocity would be distance over time. Here, we're looking at change in distance over change in time. Change in distance is also sometimes called displacement. So here, the average velocity we can calculate basically using the slope formula, even though we wouldn't consider it a slope. This is not a geometry problem. It's a physics problem. And the function here represents position, not height, but we could interpret it that way if we made a graph. So here, change in distance over change in time gives us a very familiar formula. This difference quotient, which you can think of it as the slope of the secant line. So this is the average velocity over a time interval that's length h. Now, using the limit, so the limit's a very powerful intellectual idea. We want to try and find not the average velocity over a time interval from 5 to 10 seconds or 5 to 7 seconds. I want to find the velocity over an interval that's from 5 to 5 seconds. I want to find the velocity at a single instant. I want to find what's called the instantaneous velocity, or sometimes a lot of books drop the phrase, they just refer to it as velocity. Technically, it's instantaneous velocity. And here, as I said, instead of an interval from a to a plus h, I want to look at the interval from a to a. So I send h to 0 in this formula. In this formula, to find the velocity at a single instant, let's send h to 0. That makes the interval go from a to a plus h to just a to a. We're at that single moment in time. And so using math, we've sort of stopped time. We've managed to capture information that's happening at a single moment of time. If you've worked with time, you know that it's very difficult to stop time or capture anything in a single moment of time. In fact, a single moment of time doesn't exist, right? There's no such thing as a single moment of time. It's like a river that's moving. You can't stop the river. There's no such thing as a single moment of that river. It's constantly flowing. It's constantly moving, but with a limit and calculus, we're able to capture what's happening at this single moment of time. So it's really quite remarkable. And here I wanted to repeat the approximation idea, that using the derivative now, we can approximate f of a plus h, using only information about the function at a single point and the derivative of the function at a single point. So look here, we only have 2 pieces of information. We don't even necessarily need to know what the function is. I just need to know what f of a is and f prime of a. And then I can start approximating f of a plus h. And just to remind you where this formula came from, because sometimes it's a little confusing here, if we replace, remember, I'm assuming f prime of a is approximately equal to this thing that's called the difference quotient. Oh, I need to get rid of that limit too. So here, I'm assuming f prime of a is approximately equal to this difference quotient, and then solve for f of a plus h. So finally, one comment, that I'll make is the derivative is actually a vector. It has magnitude and it has direction. So if the derivative is positive, typically that means we're moving to the right. If the derivative is negative, typically we're moving to the left, okay? So the derivative is actually a vector, and I'll talk about that in more detail later. And here, if we take the absolute value of the derivative, basically finding the magnitude of the vector, that's called the speed. And that has no direction attached to it. It's just a magnitude. So in general, we interpret the derivative to be the instantaneous rate of change of y with respect to x. And it was really helpful to think about the units when you're doing applications. The units will help us understand what the derivative is regulating. Miles per hour, miles per gallon, dollars per year. That helps us to understand what the derivative is regulating. It's regulating a relationship between two different units. And so once we know the units, that helps us kind of think about it. So here, I just, at the end here, have a couple of examples. So let me see if I can't finish this slide and I'll stop. These examples are pretty artificial. It's just kind of reviewing the concept of using, position and velocity. So here we have a rocket launched from the ground, and we're given the rocket's position function. So at any time t, I know the height of the rocket. So we're asked to find the velocity. And that is to say the instantaneous velocity. And so we know from the previous slide, that's a derivative. And so here, from the previous slide, we want to do the derivative of the position function, because that's the instantaneous velocity. Here you can use either formula. So here we had before, instead of t, we had x. Okay, now since the independent variable is time, instead of using x, instead of using this squiggle, we're using this squiggle. But it's still the same. It kind of looks like an x, it's still just a placeholder. So this is our limit, f of x minus f of a over x minus a as x goes to a formula, but just in terms of s and t. So here I plugged in the functions, and now what I did was I combined the like terms. Anything that was multiplied to like a first order term, like 160t and 160a, so that's first order, I combined those. Anything that was multiplied to a second order, like quadratic term, like 16t squared, the minus 16a squared, I combined those, I put those together. And then I noticed here t squared minus a squared, I can factor it as t minus a times t plus a. So I did that. And now we can cancel. If you notice, there's this common term, t minus a, and t minus a in the denominator. You can factor and cancel. So we're left with this expression. And now I do the limit, direct substitution. I plug the a into the t, and so I get my velocity at any time a, at any time t equal to a, is 160 minus 32a. If you want the velocity at any time t, just replace the swiggle a with, the swiggle for time. So in general, this is just the velocity at any time t, as opposed to at any time a. So yeah, this is kind of more just practicing how we do the limit. In theory, we will learn shortcut rules, and you'll be able to do the derivative just by looking at the function. Just by looking at the function, you'll say, oh yeah, the derivative is 160 minus 32t. So here, this is really still about practicing the limits and just thinking about the concept here. So I ask a follow-up question, what's the maximum height reached by the rocket? So this uses the geometry of the information that's given. Here, if you look at the position function, it's a quadratic, so I know it's a parabola, but it's got a minus sign in front. So I know here the trajectory is going to, look something like it's going to be a parabola, you know. And so I know that it'll reach its maximum height. You can see from the graph here, it'll reach its maximum height when the slope of the tangent line is 0. Here, the slope of the tangent line, the curve represents position. So here the slope is velocity. So it'll reach its maximum height because of the parabolic shape when the velocity is 0. So I set the velocity to 0, and we solved for velocity in the previous slide, and I get that t is equal to 5 seconds. And so when t equal to 5, I can plug that into the position function, and I can determine that at t equal to 5 seconds, the rocket reaches its maximum height of 400 feet. And remember here, the parabolic shape of the trajectory is very important. That's how I know the peak is happening when the derivative is 0. So I'm going to stop right here. Remember, chapter 2 will not be on the test next week. So, don't worry about that. So yeah, let me stop right here.